Hello, welcome to Pipeline Integrity, Gamma Exponent Model Validation Part 6. My name is Colin Scott. I'm a Pipeline Integrity Engineer based out of Calgary, Alberta, up in Canada. Today what I'm going to show you is what I call my Gamma Exponent Model Megavalidation. If you've seen videos numbers 1 to 5 in this series, you'll see that I did a validation of my Gamma Exponent model against various flaw types. In the first video I looked at axial surface breaking cracks. Then I looked at stress corrosion cracks with a crack shielding factor included. The third video was corrosion and metal loss. The fourth was on circumferential cracks, and the fifth was on through-wall crack analysis for leak-rupture boundary analysis. Now what I'm going to do here is I'm going to take all those 5 data sets and I'm going to pool them all together and do one big mega model validation to demonstrate that the overall sort of collective behavior of the GEM is pretty good. Now, GEM stands for my Gamma Exponent Model, and here we have it in its mathematical form. Those of you that are in the business will see that it's got a very similar mathematical form to the original log-secant model, which was developed back in the 1970s by the Battelle Institute in Columbus, Ohio. The NG18 committee did a lot of work in this field. Key thing with the GEM equation is it's mathematically derived with a focus on crack depth. The focus here is on surface breaking cracks and surface corrosion, and we want to understand how pipes are going to fail in the depth direction. The original log-secant work that was done in the 1970s was all focused on length, and the reason for that was that the original work looked at through-wall cracks first, and length is obviously the more important factor there. But the GEM has taken a little bit of a change since then. Okay, so starting from the left, I've got the remaining strength, which is the predicted failure strength over the flow strength. Then we have a remaining ligament term to the power of the gamma exponent, 2 over pi. We have an arc-cos exponential term. K squared is the material toughness. There's a 10 factor in there. A is the crack depth, and then we've got our flow strength there squared. Now, the gamma exponent for crack-like flaws is defined as the minimum of the crack length, 2c, divided by the pipe radius. But that's only taken up to a maximum of 1. You could have the longest crack in the world. It could be multiple diameters in length, but you would only go up to 1 for your gamma exponent there. There is some fine print on the model, but I really need to address situations with various flaw types. So I hope you'll bear with me here. The original GEM validation, the original GEM derivation work was essentially a flat plate solution. So in order to use it for pipe, we need to specify thin wall pipe of about D over T of 20 or more. That's a somewhat arbitrary value. I think if you go to smaller pipe and thicker wall, you'll probably end up with extra conservatism in your assessments, but that's a work in progress. The flow strength I've used for all of my validation work is the yield strength plus 69 megapascals or 10 KSI. I did not shift around looking at the various different flow strength definitions out there. Those of you that like to tinker with numbers might want to try that. The flaw depths that I'm using can be modified by pi over 4 to approximate a semi-elliptical profile. So I would do that for, say, a stress corrosion crack or a fatigue crack, which would very likely have a thumbnail type profile. I would also use the semi-elliptical profiles for sort of generic localized metal loss in which I didn't have a full flaw profile. I have developed a level 2 algorithm which I've nicknamed the ELM, and that can be used for more refined predictions if you do have a full flaw profile. I've been able to do validation work with that level 2 algorithm on metal loss flaws, but I don't have the data yet to do that on crack-like flaws, so just be aware of that. The flaw depth can also be modified by an additional 0.63 or 0.84 if I'm doing some axial stress corrosion cracking work, and that's to account for crack shielding effects. Those numbers of 0.63 and 0.84 were not pulled out of thin air. There actually is a technical rationale, but it's a little bit complicated, too complicated for today, but I will be putting together a video sometime soon that explains how I've derived those values. Okay, the gamma exponent is limited to 1/2 for metal loss, and that's a little bit unusual. There are technical reasons for that, which are outlined in my ASME Journal of Pressure Vessel Technology paper. The limit for all my other flaws is 1, as I mentioned earlier. The toughness used for this validation work was the lower bound Wall-and-J-Sharpie correlation, or in some cases I had CTOD data, so I used the J equals M delta yield strength basic equation using M equals 2 for plane strain conditions. Now I need to say that using the typical Sharpie over area correlation for toughness is really not recommended. I know that a lot of people use it for log secant model, or you might use it for Corlas model, but I've got some pretty strong feelings on why it should not be used sort of recklessly. In order to understand that, you need to go see my other pipeline integrity series. It's called Things That Make Me Go, and it's video number 4. I give you an explanation as to why I think that Sharpie over area is not necessarily what we think it is. Circumferential flaws are typically tested under bending conditions, and so I've done some development on a correction factor. That's a work in progress, so please bear with me with that. And at this point, the gem is not recommended for cold welds or grooving corrosion. I haven't been able to find appropriate data to do the validation effort properly. Now, if you've seen videos numbers 1 to 5, you've seen I've done a lot of validation work. I have 64 axial crack-like flaws that were laboratory machined. I've got 24 axial crack-like flaws that are ex-service, like metallurgical, fatigue flaws, and hook flaws. I have 9 stress corrosion cracks. I have 85 corrosion or metal loss flaws, 23 of which I've got full profiles for. I have 26 circumferential crack-like flaws and 92 through-wall cracks for leak-rupture boundary analysis. So the grand total is like 300, or close to 300. Now, the full details of where I got all those numbers is provided in the other videos. Some of you might want to do a little follow-up study, and you can get the full references in those other 5 videos. So here's what happens when I take all of those different types of data and I do an overall mega gem validation. Here on the y-axis, I've got the gem predicted failure strength. And in that case, I've included bending factors if necessary. I've included depth factors if we have semi-elliptical flaws, and I include an SCC crack shielding factor in the case of SCC. So everything I've just mentioned in the fine print. And then on the x-axis, I've got the true measured failure strength. And when you look at all of these data points, you'll see that they are pretty well grouped along that diagonal, meaning that I've got pretty reasonable accuracy. There are some data points that are above the line, and these represent non-conservative predictions, so that would represent unsafe predictions for the pipeline operator. But those are balanced out fairly well by the data points that are below the line. The data points below the line are overly conservative, and that's safe for the pipeline, but it's potentially very expensive for the pipeline operator if they're doing repairs that are really or not necessary. Now, I've made the point in a couple of my other videos that my goal with the GEM validation is to try and get a very accurate model. There are some people that would argue that you want to have a conservative model, but I don't agree with that. If you have a conservative model but you don't understand why it's conservative, you're really just introducing more uncertainty into your pipeline integrity program and all of your reliability calculations. If you can focus on finding an accurate model, then you know that your mathematics are correct, and if you've got confidence in that, then you can apply conservatism such as a lower bound yield strength or a lower bound toughness value. You can add a tool tolerance to your crack or corrosion depth measurements and such. But really, having all your data points line up right on the money is, in my mind, really, really important to demonstrate that you've got good mathematics behind your underlying model. I think I've got that pretty well here. If I go and look at the statistics for this Megavalidation study, what I do is I describe the accuracy in terms of the mean of the failure ratios. And the failure ratio for each data point is going to be the true failure strength, as measured in the lab or through a service failure, divided by the GEM predicted failure strength. Now, when I take all those 300 or whatever data points, and I come up with the mean of the failure ratios, I get to an accuracy of 1.04. So that means that overall the model is a little bit overly conservative. So that gives a little bit of comfort. But it's also very close to 1, meaning that I've got pretty good confidence that the mathematics behind the model are inherently sound or pretty close to being sound. The precision, which I define in terms of the standard deviation of the failure ratios, comes out at 16%. Now, those of you that study other models will probably see that this 16% is about as good as you can get for individual data sets. Overall, I'm not aware of any models that have been used on 300 data points with different flaw types and achieved a combination of accuracy and precision like this. So I'm really pretty pleased with the direction that this model has taken. Obviously, some people might have data sets that I'm not familiar with, and maybe those data sets push things in a different direction. I'd certainly be open to receiving data sets from anybody that was interested in further validation. Now, I've decided to do a little study to see, even more whether this is mathematically legitimate. And so what I've done is for each one of those data points, I've determined a failure ratio. And I want to ask the question of, do those failure ratios fit a normal distribution? So what I did is I took all those 300 data points and I put them in order of lowest failure ratio, meaning the most unsafe prediction, and I put those all in order all the way up to the highest failure ratio, meaning the most overly conservative. And then what I've done is I plotted those values as a cumulative frequency distribution to see if it fits into a normal curve. And then I also want to know, are there any trends in that failure ratio when I plot as a function of pipeline diameter or wall thickness or strength or toughness or length or depth? If you can plot those failure ratios and you find that there's a very distinct trend one way or the other, that really points towards there being a mathematical snafu buried somewhere in the mathematics that needs to be looked at. So I'm trying to cover all the bases in terms of demonstrating that the mathematics are legitimate. Now here's what happens when I take all those 300 data points and I plot them as a cumulative frequency distribution. Now you'll see that I've got a pretty good S-curve here. Now I have to admit that when I compare that against the perfectly normal distribution, that gray dashed line that you can see kind of in the background, the data points do not fit this 100% entirely perfectly. But I will say, in the great scheme of things, I'm not losing any sleep over this. If you actually look at the data points between a failure ratio of about 0.75 and about 1.25, which is really the critical zone, you actually have a slightly better precision than the numbers would imply. You're actually a slightly tighter distribution within that zone. So I feel pretty good about that. Where you balance that out is in the failure ratios that are over 1.25 up to about 1.50 or 1.75. You'll see that's where you've got a little bit of an offset there. In the great scheme of things, I'm very, very pleased with this. Now here's what happens if I plot all those failure ratios on the y-axis and I plot against diameter on the x-axis. You'll see that there is a slight slope in that trend line, but when I look at the mathematics, it's less than 1% across the spread of diameters, and the r-squared value on that is 0.03. So from a statistical perspective, I can't say that there's any effective diameter, or it's pretty minor. I can also do the same thing of failure ratio plotted against wall thickness. Again, if I look at the slope of that line, it's 0 or close to it. I've got an r-squared value there of 0, indicating that there's no correlation between the failure ratio and the wall thickness. I could keep going through various other tests. Failure ratio against yield strength. There I do see a little bit of an effect, r-squared of 0.04. I suspect that that might be due to my definition of flow strength that I've kept fairly constant. If I were to play around with those definitions of flow strength, I might be able to tweak that curve a little bit, but I'm not losing any sleep over it. If I look at the k-squared toughness value here, again, r-squared equals 0.00. So it's basically indicating that the model prediction is not influenced by what the toughness is. It's equally conservative pretty much everywhere. Do the same thing for length. Length, I do see that there's a little bit of conservatism as I get to longer and longer flaws, but again, r-squared value of 0.02, that's not worth losing any sleep over. I can look at the flaw length ratio where I've essentially normalized it to the flaw radius because that's what I tend to do. There I see a minor effect of about 5%, but the R-squared value is 0.05, so it's really not a meaningful statistical trend. If I look at the flaw depth here, about a 2% difference from across the plots. Again, R-squared of 0.05, it's not a meaningful correlation. And same with looking at the flaw depth ratio, R-squared of 0.02, it's not a meaningful correlation. So when I look through all of these plots, in every case I'm getting an R-squared value of 5% or less. So that's essentially telling me that there's no definitive statistically verifiable correlation between the failure ratio, so the conservatism in the model, and any one of these different factors, whether it be the flaw depth or the strength or the diameter or the wall thickness. So that makes me pretty confident that the underlying mathematics of the gem is pretty good. If you're interested in seeing some more videos, I do have 6 videos that are under the title of Pipeline Integrity, Things That Make Me Go, parts 1 to 6. And that video series is a critique of the NG18 based assessments for both corrosion and cracking. Those equations that were developed 50 years ago are mathematically focused on the length. Length is important for the through-wall crack assessments, but it's not important as much for the surface breaking cracks or the surface corrosion. My feeling is, from a mathematical perspective, any failure prediction models for surface breaking flaws really should be focused on flaw depth, and that's what I've done with the gem model. If you dig up the other 5 parts of this video series, Pipeline Integrity, Gamma Exponent Model Validation, you'll see the detailed assessments of circumferential cracks, axial cracks, SCC, corrosion metal loss, and axial through wall. So you can see each one of those 5 different flaw types assessed individually, and I give you some simple statistics to show you that the gem model, with its different little tweaks here and there, is working fairly well for all different types of flaws. If you prefer to do some reading, I do have some peer-reviewed papers here. Please help yourself. For the mathematically minded people, I would suggest going to number 3 there. That's the ASME Journal of Pressure Vessel Technology paper, which goes through the full detailed mathematical derivation of the gem model. I demonstrate that it's very similar to the log secant model from 50 years ago, except that it's focused on depth rather than length. And if you've made it this far, thank you very much for your time and your attention. I hope I've given you something to think about. From my perspective, the gem model is validating very well with the 300 data points that I've got. I'm certainly open to validating with other data points if anybody wants to provide them. Thank you very much for your time. Till next time. Bye.